Hello everyone, I am Momeni. I'm currently doing a postdoc in geoenergy lab at EPFL in Lausanne. I will talk about combining active and passive acoustic methods to image hydrofracture growth in laboratory experiments. As we know, hydrofracturing is a common tool for industries like oil and gas, geothermal energy, CO2 storage, and so on, to enhance their productivities. Physics of hydrofracturing has been studied in details using simulations and laboratory experiments, mostly on transparent material like PMMA. However, in rocks, acoustic signals are the most common ways of studying the spatiotemporal growth of hydrofractures. There are two techniques that acoustic signals can help us to study hydrofractures in rocks. One is active scanning and the other one is passive monitoring. Active scanning gives us mostly information about the fracture front where the P waves will be diffracted, while passive monitoring gives us information about the cohesive zone and especially the process zone where active monitoring cannot capture that. Here in the lab, we combine the two methods to get the best resolution image of the hydrofracture growth in rocks. Our setup consists of a polyaxial confining stress that provides a triaxial stress regime using flat jacks. The fluid has been injected into the sample, rock sample, through the injection line. So the block has been drilled from the top to the center and a notch has been created to facilitate the nucleation of fracture. A needle valve is set on the way to ensure the toughness-dominated hydrofracturing test. And after that, there is a pressure transducer that helps us to estimate the amount of fluid that has been entering the fracture during the experiment. As I told, we have two measurement systems. The active measurement consists of 32 pairs of source receiver, which 54 sensors work for P waves and the other 10 work for S waves. They are shown in red and blue circles here. Most of them are set on the top and bottom platens. And each active source does the excitation in a frequency usually close to 750 kilohertz and repeats the excitation for 50 times, so that the signals that are received by the receivers would be stacked to have a better signal to noise ratio. So usually one active scanning takes about 2.8 seconds. And their recording sampling rate is 50 megahertz. Parallel to active measurement, we have the passive monitoring that are shown in green triangles. They record continuously with a sampling rate of up to 12.5 megahertz. And of course, they are saturated when the active measurements are happening. Here, I explain the results of a Gabbro test. It was a Zimbabwe Gabbro that had a low porosity and the grain size was about 1 to 3 millimeters. The other physical parameters are mentioned here, and the P-wave velocity was about 6,740 meters per second. We inject the glycerol, and the confining stress were 20 megapascal on the horizontal directions and 10 megapascal on the vertical direction to ensure the horizontal growth of fracture. And the injection rate was 0.04 milliliter per minute. So this test was designed to be in the toughness-dominated regime. From active signals, we are able to read the diffracted P waves from the fracture front. And these arrival times give us the location of fracture front at that time. Using a nonlinear Bayesian inversion algorithm, we are able to reconstruct the fracture front at that time. And we can estimate its shape using ellipse or circle. Here, for this test, we were able to reconstruct 20 snapshots during the experiments that last about 3 minutes. And of course, as much as the source receiver pairs are higher, we have a better result. In this test, we had a resolution of about 2 millimeters for reconstruction of fracture fronts. We developed a passive monitoring algorithm that processes the passive data and reads the p-wave arrivals and associates the correlated signals as potential events. And using a two-step 3D search, we look for the most probable hypocenter location for the acoustic emissions. So using this technique for this 3 minutes of data that has been recognized as the fracture duration, we were able to locate over 6,000 of acoustic emissions that about 1,600 of them had location error of less than 2 millimeters. Combining the active and passive results, we observed that the fracture has been planar and growing almost horizontally. And the number of acoustic emissions has been rising when the downstream pressure dropped, which was the sign of fluid entering the fracture. And of course, there are some acoustic emissions that occur before the main drop of downstream pressure as precursor to nucleation. And the estimated fluid that has been entering the fracture has two fluctuations, showing the approximate time for the start of the fracture and the end of it, where it's reached to the end of block. And there is direct relation between the number of acoustic emissions and the speed of the fracture front. Of course, passive acoustic emissions that are shown in red dots are ahead of active measurements that show the fracture front, because these are showing the fracture process zone. So with this technique, we are able to capture the spatiotemporal growth of fracture front and fracture process zone during hydrofracturing experiments in the laboratory scale with a resolution of about 2 millimeters. These techniques can help us to better study the physics of the hydrofracturing phenomena, and the explained passive algorithm can be used as field for microseismic monitoring and for seismic hazard mitigation. Thank you.